Yeah, thank you very much. Thanks everybody for being here. Thanks for the introduction. Thanks for your kind words, Elias. In today's talk, I wanted to talk about some recent work that actually does relate to my dissertation work, as you're going to see, and also the foundations of deep learning. And I will present some theorems and then maybe some philosophical corollaries of this work for deep learning. So, yeah, without further ado, is that a question in the chat? Okay, good. Without further ado, let me introduce a motivating question for the discussion today, which is the following. So on the left-hand side, you see maybe a photo you've already seen of AlphaGo beating Lee Sedol in Go, a very hard board game. On the right-hand side, you see a Waymo car, which is trying to enter a highway, but it's being antagonized by human drivers. So much so that it abandons the attempt, exits the highway, and tries again. So the motivated question is, how is it that machine learning models beat humans in Go, which is a very hard game, but cannot enter highways, which is a game that all of us are good. Most of us, at least, are okay, at least in doing. So the topic of today's talk is optimization methods in machine learning, and an oversimplified view of the remarkable progress that has happened in recent years in deep learning is that a lot of that progress is due to the fact that we are now able to optimize very complex models. So it's our ability to write down a very complicated model, a prediction model, and use data to train it. So we're able to do gradient descent on that model. And of course, it's not just the fact that we can do gradient descent. It's a lot of other things like the right inductive biases, having good hardware to do our gradient descent, having a lot of enough data to train our model, and so on and so forth. But from at least the optimization standpoint, and a remarkable empirical finding is that in several interesting learning settings, gradient descent or its variants discover local minima, and B, those local minima generalize well for their learning task. So that's a simplified view of the world, describing the remarkable progress in deep learning in recent years. Sort of like the motivation for this talk is that nowadays, and certainly down the road as we deploy more and more deep learning, is that, or more generally, learning agents in the world, is that we are expecting to have multiple learning agents that are interacting in the same environment, as well as interacting with each other. And the question that arises is the following. If you launch a learning agent in some environment where you expect it to interact with the environment itself and also other agents that are interacting with the environment, what training method should you endow your learning agent with? And unfortunately, the practical experience is that doing gradient descent against another gradient descent, or maybe multiple other gradient descents, has a very hard time converging, let alone converging to some meaningful solution. And in particular, if sort of like you endow your learning agent with gradient descent to consume data from the world, using that data to train its own policy, to then make actions that will then influence other agents' experiences and actions, and so on and so forth. So our practical experience is that a gradient descent isn't such a good algorithm anymore. And what I would like to study in this talk is how deep mathematically and computationally this issue is. So I'm expecting applications in the future to involve multiple learning agents. So in general, I'm very interested in equilibrium learning type of problems. And of course, the baby version of equilibrium learning is the case where you have two agents. So that's the first step away from the standard learning settings where we have a single agent. And in particular, the focus of this talk will be min-max problems involving a min player and a max player who share an objective function. So which the min player is trying to minimize and the max player is trying to maximize, but their actions are entangled in the objective function f. So, of course, the first idea for solving such problems when x and y are multidimensional is to have the min player and the max player run gradient descent or some variant of gradient descent in parallel. So, so vanilla gradient ascent for this problem would be that the x player is doing gradient descent since it's trying to minimize the function f, while in parallel, the max player is trying to do gradient ascent to maximize the function. And these decisions are interleaved, these online learning procedures are interleaved in some way. So people in practice try gradient descent, variants of gradient descent. Sometimes they have, one of the players do fewer steps for, every, like have one of the players do multiple steps for every one step of the other player and so on and so forth. So people are trying hard to solve min-max problem of this form. But as I said earlier, the practical experience is that these are very hard problems to solve with gradient descent procedures. And here in these two pictures, I'm just showing two examples from training GANs, so generative adversarial networks, where in one case, so here, training a GAN to generate digits from the MNIST dataset eventually converges to some fixed distribution over garbage symbols. So gradient descent fails to generate from the target distribution. In the bottom figure, you're training a GAN on a mixture of Gaussians, and if you stop the training at different steps, and you see what types of samples the generator is generating, you see that sort of like the generator is moving from mode to mode of the distribution, and it never settles. And these are just examples of some particular way to implement the gradient descent ascent dynamics. And the difficulty of training GANs has motivated a lot of work on tricks to make gradient descent more converging in this specific application. But there, I think it's reasonable to say that min-max optimization is hard for gradient descent, and that more broadly, equilibrium learning is a quite open problem. So there are no general purpose optimization procedures that work reasonably well in these types of multi-agent learning settings. And this is the motivation of this talk. So we want to understand, are there any fundamental barriers towards obtaining such optimization procedures? So in particular, our focus of today is going to be a very narrow special case of the broader equilibrium learning problem, which is understanding the difference between minimization problems, where you're trying to minimize a function f over some domain, versus min-max problems, where you're trying to minimize some function fxy over some domain that entangles x and y, that constrains x and y. And we're going to focus on the case where we're not going to place more assumptions about the convexity of f. So we're going to study both problems and compare them in the setting where f is Lipschitz and smooth, but is not going to be convex for the left-hand side or convex-concave for the right-hand side. The constraints are going to be convex and compact. So let's try to compare these two problems. Again, so far, deep learning has been operating on the left-hand side. But once you consider GAN training or broader two-agent settings, you easily arrive at min-max problems. And, again, there are, even broader problems, as I've already described, that take the form of equilibrium learning. So let's compare what we know about these two problems that we focus on in this talk. So in the early years, and by early years, I mean, 20th century, we considered very specific, mostly very specific versions of minimization and min-maximization. On the minimization side, we consider the case where f is convex, which is, of course, a much better behaved setting. On the min-max side, starting from von Neumann and mathematical programming duality, we have been focusing on convex functions fxy, which are convex in the minimizing, the argument x, with respect to which we're minimizing, and concave with respect to the other argument y. And in these two settings, the two problems are quite similarly behaved. So on the left-hand side, standard results from optimization theory say that first-order methods find approximate minima in a number of steps and queries to the function f and its gradient that are polynomial in the approximation, the smoothness of the function, and the diameter of the set with respect to which we're optimizing. And essentially, the same results apply to the right-hand side. Again, first-order methods, which access f through its values and its gradient values, can find approximate min-max equilibria in a number of steps and queries that are polynomial in the approximation, the smoothness, and the diameter. And just to be explicit about what are the approximate solutions I'm talking about, on the left-hand side, an approximate minimum is a point x star, which cannot be improved by more than epsilon by switching to some other point. On the right-hand side, an approximate min-max equilibrium is a point x star y star, which cannot be improved by the min player or the max player by switching to some other x or y. So the minimizing player cannot change x star to something else to decrease the function by more than epsilon, which is what this constraint is saying. And the maximizing player cannot switch y star to some other y to increase the function by more than epsilon, which is what this constraint is saying. Okay, so again, if the function f is convex on the left-hand side, very good algorithms exist. If the problem is convex concave on the right-hand side, very good algorithms exist. And there's no clear difference, at least in this viewpoint, between the left-hand side and the right-hand side. But again, the focus of this talk is not that nice convex problem, but the case where f is just Lipschitz, but is not assumed convex or convex concave. So what happens in this setting? Well, the answer is easy. Okay, so the problem is NP hard. So what are you trying even to achieve? Okay, so the problem is hard. So minimizing arbitrary functions over a convex domain is a difficult problem. It's NP hard. min-maximizing arbitrary functions over convex domains is NP hard. So what are you trying to achieve? So that's the answer of, or at least used to be the answer from coming from theoretical computer science. But so deep learning came along and said, whatever, just go for local optimality. So this is the focus of this talk. So what if I want to find locally optimal solutions to the left-hand side or the right-hand side? Well, as far as the left-hand side is involved, if you switch from global min to local min, nothing much changes. So if your function f is arbitrary and you're looking for a local min, then you can still, you still have first order methods that find approximate local minima in a number of steps and queries that are polynomial in the approximation, the smoothness, and the diameter of the set. So the min problem doesn't care about whether f is convex or not, as long as you're looking for local approximate solutions. So the goal of this talk is to understand what happens to the right-hand side if f is not convex concave and I'm looking for local equilibria. So the main result with Stratis Skoulakis, who's a postdoc at SUTD, so in Singapore University of Technology and Design, and Manolis Zabetakis, who was my PhD student at MIT and is currently a postdoc at Berkeley with Mike Jordan. So what we show is that first order methods need exponentially many queries to f and its gradient to find approximate local min-max equilibria. In particular, the lower bound is exponential in at least one of the approximation, the smoothness of f, or the diameter of the set. I will precise about what approximate local min-max equilibria mean and what approximate local minima mean for the left and the right-hand sides in a little bit. But now I'm stating the results, and I'm going to dive into that in a second. We also show that, so the first theorem is unconditional. It says, regardless of, what is your religion with respect to computational complexity, you need exponentially many steps to find approximate local min-max equilibria. If you believe that polynomial time is different than a complexity class called PPAD, which I will explain later in the talk, then no algorithm, first order, second order, or whatever, can do so in polynomial time. So any algorithm will have to take super polynomial time to find approximate local min-max equilibria. So these are the main results of this talk with Stratis Skoulakis and Manolis Zabetakis. And the plan for the remaining of the talk is to be even more precise about what approximate local min-max equilibria are and where they're coming from, and also give you a flavor of the result and the proof. Any questions at this point?
Matt, one quick question. Maybe you'll get to this later. Can you just say why the second result doesn't follow as a corollary of your work on Nash equilibria? Like, what is what's different here?
Yeah, that's a great question. This problem here is a zero-sum game. So in my work on Nash equilibria, we proved hardness for general sum games. So games where the one player had his own objective and the other player had her own objective. And it is a priori unclear if zero-sum game. So here you have two players that are sharing one objective that one is trying to minimize and the other is trying to maximize. So, or in other words, the min player is paying the max player fxy. So the max player is trying to maximize the money that they get from min. The min player is trying to minimize the money that they pay to max. So it's unclear if such zero-sum games, if you allow the objective function to be non-convex concave, if they can actually implement the full complexity of PPD. So that is, in fact, that is an important sort of like question that that we had before starting this work, and doing this work, it helped us clarify what makes zero-sum games hard if you remove the convex concavity of the payoff function. And I hope to get to that later in the talk. But that's a great question. So another way to view the PPD completeness result is to say that zero-sum games are as hard as general-sum games, as long as you take the zero-sum objective and make it non-convex concave. Of course, as I was saying earlier, if the objective is convex concave, then zero-sum games are easy to solve.
There is another question. Let me see if I can unmute. I mean, I think you can ask your question now.
Okay, thank you very much. So Kostis, I have just a question. When you say local minima, you talk about the stationary points or local minima?
Yeah,
because
so
local minima can take exponential time, even for not to
that's
this,
right.
So
That's right. So right. So on the left-hand side, where I'm talking about an upper bound, I'm talking about first order local minima. So station like places where the gradient is small. So on the left-hand side, and you're right that if I wanted second order or like higher order, yeah, if I wanted to certify that something is a local mean, that's a much harder problem. Right. Of course, this is not my result, and the focus of this talk is at the right-hand side. So for the purposes of the lower bound, I'm even going to show a lower bound for first order local min-max equilibria, which of course is stronger than a second order or higher order. Yeah, that's a good question, and I will clarify exactly what I mean. But yeah, so first order, everywhere first order for the remaining of the talk. Okay. Yeah. That's a good question. Yeah.
Thank you.
Thanks, Amin. All right, so let me move on, and I'm going to stop again for questions. All right, so we're looking at non-convex, non-concave objectives, and like the first question you should ask before actually trying to prove a theorem is, what the heck is even the goal if the objective function is not convex concave, non-convex concave? So, of course, as you know, if I make no assumption about the convex concavity of a von Neumann's theorem breaks, and it breaks in various ways. So, if the x and the y, if the sets with respect to which you're optimizing are compact and stuff, convex and compact, both problems are well defined, but they could be different. So here's an example where the max mean is different than the min max. So the order of the mean and the max player matter if von Neumann's theorem breaks. For other f's, equality may hold, but there could be multiple disconnected solutions. So in general, generally speaking, if convex concavity is dropped, the behavior of the problem changes a lot compared to the case considered by von Neumann, where again, min max equals max mean. So the order doesn't matter. And also the case where the solutions are a convex set. So when it's not convex concave, there could be the min max may not be equal to the max mean, and also the solution set could be disconnected. So everything breaks. All right, so if everything breaks, what's even the goal? So that's a very natural question to ask. So again, here is my problem. Min max of a function xy in some convex compact set Function f is just continuous. The set is convex compact. This is the problem I'm trying to solve. And there are various ways, various types of solutions you may want to consider. Okay, so one is the global mean, global max solution. It's well defined under my conditions here, but it's going to be NP hard to find. So let's compromise for local solutions. So what types of local solutions may we consider? To define them, let me make on the side a couple of useful definitions. So if I have a set S that constrains X and Y, I'm gonna use this symbol S X dot to represent all the Y's that are compatible with this specific X. So all the Y's for which X and Y are in the set, while X subscript X capital are all the X's for which there exists some Y that are feasible. And similarly, I define X dot Y and S subscript Y capital. Okay, so these are some useful definitions. Now, what compromises might one consider if they don't want to consider global mean, global max solutions? So one compromise is to have the mean player be local and keep the Y player global. So the outer player local, the inner player global. So a local mean global max solution is a point X star Y star that is feasible, and for which for some radius delta, you have this inequality hold. So let's parse it. So any Y cannot increase the function. So any Y that is compatible with X star cannot increase the function. So the Y player who is globally optimizing cannot improve the money that they receive from X, from the mean player, even if they consider global moves. That's why it's called a global max solution. It's called a local mean solution if the X player cannot jiggle the X in a way that after the Y player globally best response, function f decreases. And this is what's expressed by this inequality. It says that if I jiggle X star to some X, and so locally to within a delta neighborhood of X star, so if I jiggle X star to something local, and I let the Y player best respond, the function value doesn't decrease. So this solution here has the following features. It considers global moves of the Y player and only local moves of the X player. And it also takes into account the sequentiality of the decisions of the two players. So the mean player, who is the outer player, is anticipating the best response of the max player, which is captured by the fact that when the X star is thinking about changing his X star locally, he's anticipating the best response of the max player as captured by this maximization here. So that's a local mean global max solution. An even further compromise considered by Jean, Trapali, and Jordan is to make also the inner player local mean, but maintain the sequentiality of the decisions of the players. I'm not going to write it down to avoid cluttering the slide, but you can imagine what it is. It considers local moves for both players, and also takes into account that the mean player is considering local moves in anticipation of the best response of the Y player, but now locally, as opposed to globally. Another take on the problem is to consider the simultaneous move version of the game, where the two players are you know, that there's no sequential or there's no ordering of the moves, which was what was considered by me and Yanis Panaghias in a newspaper and Mazumdar and Radcliffe a couple of years ago. So in that what we call local min-max equilibria are points such that the X player cannot jiggle X in some neighborhood of X star to decrease the function value, and Y cannot jiggle Y star in some neighborhood to increase the function value. So this is a simultaneous version, a simultaneous local min-max equilibrium. This is a sequential local min-max equilibrium, and this is sort of like a hybrid local global sequential version. So what do we know about these notions? Again, 1 and 2 are sequential, 3 simultaneous. 1 is guaranteed to exist no matter what function f is, but it's too strong. You're considering global moves from the Y player, so the problem is NP hard. Unfortunately, 2 and 3 don't always exist. So kind of like the picture is as follows. So you have local min-max solutions. This is the sequential local version. This is the simultaneous local version. In fact, this is a broader set. If you think about the order of the quantifiers, the notion considered by Jean et al. is bigger than the one that we consider, but they both could be empty. Another type of solution concept that makes sense is to consider fixed points of the gradient descent ascent dynamic. So, if you had the two players, the min and the max, run gradient descent ascent in parallel, projected to the set, the constraint set S, you could consider fixed points of that dynamic. And because fixed points are fixed points, this set here of fixed points of GDA is guaranteed to be non-empty if function f is continuously differentiable, because sort of like its gradient shows up in the iteration. So if f is continuously differentiable, then this iteration here, this fixed point iteration, is continuous, and by Brouwer's fixed point, it has a fixed point. So in particular, this red set is non-empty. And you can also show that this red set contains the notion of simultaneous local min-max equilibria that we considered 2 years ago. So here is really the picture that I'm describing. So you have, a sequential notion, a simultaneous notion, and sort of like a fixed point of gradient descent ascent dynamics notion, and this map here shows the inclusions and what is not guaranteed to be non-empty. So really, this red set is non-empty, while these guys could be empty. And being empty is not a nice feature for a problem you're trying to solve, right? Ideally, you'd like to choose a notion that is guaranteed to exist. So, like unfortunately, these two local notions that are defined are not guaranteed to exist, while this other notion is guaranteed to exist. But what does it have to do with the problem that I'm trying to solve? Well, intuitively, it does have to do with the problem that I'm trying to solve, because sort of like, you would expect that fixed points of the GDA dynamic should correspond to stable, like to points where neither the X player nor the Y player have incentives to move. So why is there this discrepancy here between this red set that is guaranteed to be non-empty and this yellow set, which might be empty? So as it turns out, like you cannot resolve this discrepancy if you consider approximations, and just to explain, here's one way you can relax the local min-max equilibrium to also have approximation. You just add epsilons to the inequality. So I'm going to say that a point X star Y star is an epsilon delta local min-max equilibrium if it is a feasible point, and you cannot locally jiggle X in some delta neighborhood to decrease the function by more than epsilon, you cannot locally jiggle y in a neighborhood delta to increase the function by more than epsilon. So this is the notion of epsilon delta, local min-max equilibrium. And here are some observations about the behavior of this type of this notion. As delta, the radius in which you're considering deviations for the two players increases from 0 all the way to something comparable with the diameter of the constraint set. If delta, the radius in which you're considering deviations, is very small, then the problem is actually trivial. So you can argue that all points in the domain are local min-max equilibria because the jiggling is not is so small that you know, a small jiggle cannot contribute more than epsilon. You know, if the jiggle is smaller than epsilon over the Lipschitzness of the function. On the other hand, in the global regime where delta is very large, the problem is a global optimization problem. So it's NP hard. So the solutions may not exist, and they're NP hard and it's NP hard to check if solutions exist or find them. But there is a sweet spot in the middle. So if delta is below this quantity that relates to epsilon and the lip and the smoothness of the function, where you can argue that these local min-max equilibria are guaranteed to exist, and also they're equivalent to fixed points, to approximate fixed points of gradient descent ascent dynamic. So this is the regime that we consider interesting for min-max optimization. It's a regime in which the radius that you consider is not too large, so that the radius of deviations that you consider that you want to protect against is not too large that the problem becomes global, yet it's not too small that the problem is trivial. It's in the middle where you can prove that approximate local min-max equilibria are guaranteed to exist, and in fact, they are equivalent to fixed points of gradient descent ascent, projected gradient descent ascent dynamics, which is the natural algorithm to solve this problem. So just to summarize what I've been talking about, you know, in the local regime that I explained in this picture, so if delta is below a certain threshold that relates to epsilon and the smoothness, these local min-max equilibria are guaranteed to exist, and they're equivalent computationally to approximate fixed points of GDA. So the sort of like the yellow and the red circles here become computationally equivalent. They're both non-empty if you consider approximate local min-max equilibria. And hence, all of these things are non-empty if you allow approximation. So this is the regime where the problem is non-trivial, and also the solutions are guaranteed to exist, and this is the problem that I will consider for the remaining of the talk. So I'm gonna be considering epsilon delta local min-max equilibria, and I'm gonna, you know, have delta smaller than this threshold where I have guaranteed existence. Any questions about the solution concepts or what I talked about?
I have a quick question, might be naive, but so typically when you relate local optimality with a kind of a gradient, like some property about the gradient of the function, you also sometimes you need to say something about the Hessian, right? Like the fact that, you know, the eigenvalues of the Hessian need to be of the right sign. Here in this mapping that you have, that you don't seem to query to need that. Can you explain a little bit the high level reason why this is not necessary?
Yeah, so that relates very much to the question that Amin asked earlier. Indeed, this version here, the way it's written down, it looks like a local min, local max type of solution, while as you correctly say, fixed points of this map here, relate to making this gradient small or zero. So it's reasonable to ask why the Hessian doesn't play a role, because this looks like a first order type of solution. So really, like, fixed points of this are either occurring at points. Let's look at this. So where do we expect to see fixed points of GDA? Well, the obvious type is those that are in the interior of the domain, and the gradients with respect to both x and y are zero. And there are some other fixed points on the boundary, as long as the gradient is pushing you towards the boundary, so you cannot, you are fixed. So yeah, it's regardless, it's sort of like a first order type of solution. I mean, okay, so there's this boundary thing where, you could have non-zero gradients as long as they point you to the right direction. So this one looks like this is a min-max type of solution, but I guess sort of like what this epsilon allows you to do is to trade off. So effectively what happens here is that sort of like, let's look at the point in the interior where the gradient is zero. Because delta is smaller than 2 epsilon, the Lipschitzness of the gradient, this will actually satisfy this constraint. So it's very, very reasonable for you to ask why the Hessian doesn't show up. But a simple answer is sort of like, if I consider an x star, y star that is in the interior of the set, and where the gradient is zero, because I have taken delta smaller than this quantity, if I kind of like think Taylor, Taylor will show that L is a bound on the Hessian, and if I do Taylor, because the gradient is zero, the contribution of the second order is going to be delta squared times the Hessian, and over a half times a half, and this 2 epsilon lambda over there is exactly what I need, so that I get an epsilon increase or decrease.
Okay, yes.
Yeah, okay.
Thank you.
And this is for sort of like the easier kind of like mental picture is for x stars, y stars that are in the interior. So, you have to see that the boundary stuff work as well. But yeah, this is really exactly the rationale for where this threshold on delta is coming from. It's really like coming from so that Taylor for a zero gradient gives you exactly error epsilon. That's where it's coming from. All right, so let me jump into the main result. Again, so now let me summarize everything I talked about. The problem I'm interested in is I have a G Lipschitz function, lambda smooth function, and I have a convex compact set. I want to solve this problem here. And I'm interested in 2 problems. One is for epsilon and delta in the local regime where epsilon delta local min-max equilibria exist. I want to find such an epsilon delta local min-max equilibrium. So that's one problem I'm interested in. The other problem I'm interested in is to find an approximate fixed point of the projected gradient descent ascent dynamic, which is, here is the projected gradient descent ascent iteration. I want to find a point x star y star that is a fixed point of that iteration. And what I argued earlier is that these 2 problems are computationally equivalent. In particular, this problem always has solutions. Always has a solution because of Brouwer's fixed point theorem. This problem also always has a solution as long as delta is smaller than this. And you can reduce polynomial time, reduce from one problem to the other. So these problems are computationally equivalent. And in particular, to avoid carrying around this constraint on delta, I'm just going to be thinking about GDA fixed points, but again, it's equivalent to be thinking about local min-max equilibria in this local regime where they are guaranteed to exist. So these problems are hard, but how hard are they? right? So are they NP hard to solve? That is the first question to ask. And the answer, the immediate answer, is that they are not NP hard to compute, because this problem here is a fixed point computation problem. And work that has happened already in complexity theory, has shown that fixed point computation problems are not likely to be NP hard unless you get complexity theoretic collapses like NP equaling co-NP, which people don't expect to happen. So the picture is really this one. NP hard problems are out there. Polynomial time problems are down here. And there's this other class called PPAD. And we know that finding fixed points of functions and Nash equilibria in non-zero sum games are complete for this class PPAD. So because GDA fixed points are a special case of Brouwer fixed points, we know that fixed points of projected gradient descent dynamic are somewhere between P and PPAD. Right? And our goal is to understand, are they closer to P or are they closer to PPAD? So this is the point of the discussion. Now, okay, first of all, what the heck is PPAD, right? It's not the standard complexity class that we learn in high school. So let me try to define it, okay? So PPAD is a subclass of NP, or to be more precise, functional NP, so search problems in NP. So it's a subclass of NP which contains problems that are guaranteed to have a solution. And the reason they are guaranteed to have a solution is because of this parity argument that you see here on the screen. A very simple one, that if a directed graph has a node whose in degree is different than its out degree, then it must have another unbalanced node. So what Christos Papadimitriou did in the 90s is he took this very simple parity argument and created a complexity class out of it of problems that ask you to find a solution, and that solution always exists because of this simple parity argument. So he took this parity argument and defined the complexity class out of it. That complexity class was a subset of NP. And as it turned out, it contained very interesting problems, which was sort of like, and not just contained, but it characterized the complexity of very interesting problems, which was sort of like a proof that this complexity class was an interesting one. Okay? And in particular, these problems define implicitly a huge and exponentially large graph, and they show you an unbalanced vertex in that exponentially large graph, and they ask you to find another unbalanced vertex in that exponentially large graph. So this is what problems in PPAD do. And the interesting finding is that a lot of interesting problems in topology, combinatorics, and economics are complete for that class, which means that not only they belong to that class, but they are as hard as any other problem in that class. And in particular, all these problems are equivalent to each other. So the work that happened in the 90s and 2000s and still is going on in this literature has shown that very interesting problems like Sperner, Brouwer, Nash are computationally equivalent to each other, And the way these computational equivalencies are proven is by going through this complexity class PPAD. And what we show in this work is that these problems that we're interested in this work here are also complete for this class. So in particular, finding min-max, locally approximate min-max equilibria in zero-sum games with non-convex-concave objectives is PPAD-complete, in particular as hard as finding Brouwer fixed points, as hard as finding Nash equilibria in general games, right? And what is interesting about this is that, zero-sum games are more spatial than general-sum games, but what we show is they're equivalent. Fixed points of this particular iteration map are more special cases of the general Brouwer fixed point problem, yet we show that they capture all of the complexity of Brouwer, right? So it is remarkable that the fixed points of gradient descent dynamic for general functions f are as hard as the fixed points of any function you can come up with. So that, these fixed points capture the full complexity of fixed points, and similarly, that zero-sum games with non-convex-concave objectives capture the full complexity of Nash equilibrium in general games.
Costis, can I ask a question about the MP hardness that you were saying?
The PPAD hardness or the MP hardness?
Both, because it is usually a decision problem, right?
NP, yes, it is a decision problem. But F and P, so the functional NP that I alluded to earlier, is a search problem.
Oh, it's a search problem. Okay.
Yeah. So
because if you're saying that there is this, you are saying that the solution exists, right? Yeah. So how can you turn it into something about the decision, right?
It's not. Yeah. So we're not talking about decision problem complexity here. We're talking about search problem complexity. Okay. So So in the picture, that's a great question. And in the picture I showed here, we're talking about F and P. So I should have written F and P here. So finding a satisfying assignment. Okay. Not checking if it exists. Right. PPAD is like finding a Brouwer fixed point or finding a Nash equilibrium, and P is like solving a linear program. So these are, so we're talking about functional search problems, not decision problems, right? So I'm almost done with my talk. So I don't know how much time I have. So I see two options here: sort of like concluding sort of like the talk and then opening it up, or diving into kind of like the details of like, like what the heck this PPAD thing is and why min-max captures the whole complexity of PPAD. So, but sort of like the outline of the results sort of like is done. So one interesting point to make is sort of like that our oracle loyal bound, which is unconditional, it has nothing to do with PPAD or anything like that, is a byproduct of our proof of the PPAD completeness, right? So typically, lower bounds for optimization methods are obtained in different ways, but here in this instance here, we first establish our PPAD completeness result, and as a byproduct of our proof, we prove an unconditional lower bound, which is written here, that you need exponentially many queries to F and its gradient to find approximate local min-max equilibria. So here's what I would like to do next. So I want to illustrate one little aspect of the proof. It's going to be impressionistic, but it will show, or it will allude to, why min-max is harder than min-min. Okay, which is an important point, of course, because we know that min-min encounters no barriers, computational barriers here, while min-max does. So if I'm considering first order type of solutions, why is min-min harder than min-max, right? So that would be a reasonable question. I mean, as you know, was pointed out earlier, the solution that I'm considering is sort of first order, right? I mean, look at it, right? It's a first order type of thing. Why then is min-max harder than min-min? Why is turning this sign to a plus rather than a minus? Why does it turn the problem PPAD-complete? Why does it happen? Why does incur this exponential lower bounds, right? And for that, I want to give you a sense of how the proof goes and what would happen if you try to change it to a min solution, okay? And again, it's going to be impressionistic, but what the proof is trying to do is to reduce a hard problem for PPAD, in particular Sperner, into finding a fixed point of gradient descent ascent. So in Sperner, so it's a topological type of, it's a combinatorial problem, but really like the essence of the problem is topological. You have an, like you have a, finding sort of like your solution involves traversing very long paths in the domain. And what you want to do is you want to create a function f, xy, so that gradient descent ascent dynamics for that function f simulates the trajectory of long paths in that domain that correspond to searching for solutions to Sperner. So again, I haven't told you what Sperner is, so maybe this discussion is a bit out of context, but let me give you the essence of what makes min-max.
Let me just, is explaining to us what this problem is something that would take very long? I would be curious to know actually what this problem is. If I don't know what it is.
What's Sperner? No, it's not too long. It's a standard. I have some complementary slides. So it is a standard combinatorial problem. So it involves coloring a grid. So here's the grid. Here's a, you can define it in many dimensions. I'm defining it in 2 dimensions. So in 2 dimensions, you color a grid with 3 colors. In D dimensions, you color a hypergrid with D+1 colors. So here's what you do. You color the boundary of this grid in the way you see here. So the boundary coloring is important. And you use your 3 colors to color it in the way you see here. More general colorings are possible, but for us, let's fix it to be this coloring. You color the internal vertices in any fashion you want. The claim is that if you respected my boundary coloring, no matter how you colored the internal vertices, there must exist a triangle with 3 colors, with all 3 colors. In fact, there always is an odd number of trichromatic triangles. And in particular, in this picture, there are 5 trichromatic triangles. So the claim is that if you respected my boundary, then no matter how you color the internal vertices, there is always going to be an odd number of trichromatic triangles. And there is a particular way to prove the theorem and also find a trichromatic triangle. And like it's easy to explain, sort of like, let's forget where the trichromatic triangles are. You're going to define a walk that starts here at the bottom left triangle. And basically what you're going to do is you're going to envision this to be a factory. So a factory that has triangular rooms, every room has 3 pillars, and you're looking for a room that has 3 different colored pillars. And the way you prove this lemma, and that relates to the parity argument that I was talking about earlier, you say, look, let me start from the bottom left triangle. That bottom left triangle, no matter how you color the internal vertices of the factory, we know the coloring that it has because all the pillars are on the boundary. So I know it has 2 red pillars and 1 yellow pillar. In fact, I know that it has a red-yellow door it has two red yellow doors, and it has one red yellow door that I can cross having yellow on my left, and one red yellow door that I can cross having yellow on my right. So what I'm going to do is I'm going to cross a red yellow door with yellow on my left. That is going to bring me to another room. So now I enter that room through a red yellow door. If the other pillar is blue, I found my trichromatic triangle. If the other pillar is not blue, it's either red or yellow, then there has to be another door that I can cross with yellow on my left. And I will keep doing that. Now, the only stopping condition for me is if I enter a room through a red yellow door and I see the other pillar being blue, in which case I found my trichromatic triangle. The other thing that can go wrong is that I exit the factory, but there's no red yellow door on the boundary that I can cross having yellow on my left. So certainly I'm never going to exit the factory. I have to stay in the factory. Okay, so I have to stay in the factory. And the only stopping condition is that I enter a room through a red yellow door and I see blue on the other side. Otherwise, I can keep going. Okay, so that's almost a proof that there is a trichromatic triangle. The only thing I have to preclude is that I cannot kind of like loop into myself and keep going forever. But for me to sort of like wander and then loop into myself and go into an infinite loop, in the junction point, there has to be a room with 3 red yellow doors. But this cannot happen. You can think about it, but you cannot have a triangle with 3 red yellow doors. And that's the end of the proof, that there is at least one at least one trichromatic triangle. You can always start here because this room is on the boundary and you know it has a red yellow door, and then you can define a transition rule between triangles that crosses from one to the other if there is a red yellow door, and it has to be the case that you have to stop. And like in fact, I don't know, like if you want to see the full parity argument, it is glory. In reality, what I did here is I defined a transition rule between 2 triangles that goes from one triangle to the other if the 2 triangles share a red yellow door, and you can go from 1 to 2 having, crossing that red yellow door and having yellow on your left. In effect, what that does, it defines a directed graph whose vertices are the triangles. And all the vertices in that graph have in degree and out degree at most 1, because every triangle can have at most 1 red yellow door you can exit having yellow on your left, and at most 1 red yellow door that you can enter having yellow on your left. In fact, degree 1 vertices, except this special one at the bottom left, must be trichromatic. Degree 2 vertices are missing blue, so they have 2 red yellow doors, 1 to enter and 1 to exit. And degree 0 vertices are all the triangles. These are neither trichromatic nor do they have red yellow doors. So the mere definition of this transition rule defined a directed graph with in and out degree 1, all of whose degree 1 nodes are trichromatic, except this bottom left special triangle. So the graph looks kind of like this, and all the endpoints of paths are trichromatic, except this endpoint, the one that starts, the path that starts at the bottom left. And in particular, the existence of trichromatic triangles is really due to the parity argument that I described in the beginning. So finding a trichromatic triangle in Sperner's lemma, the existence of that is due to the parity argument on directed graph. You define the graph in the way I specified, and you point to a vertex that is in balance, that has different in and out degree. So the parity argument tells you that there must be another one, and the way you define your graph, that other one must be trichromatic. So Sperner is an instance of those problems that always have solutions, and the reason they have solutions is because of the parity argument on directed graphs. So now I claim that Brouwer is another such problem. And Nash equilibrium is another such problem. And the new results that we have is that these problems that we're interested in are as hard as these other problems. So everything is equivalent to each other. Okay. So we characterize exactly the complexity of zero-sum games for non-convex-concave objectives. Yeah, so let me not kind of like try to show you some pictures I had for why min-max is harder than min-min, because I don't want to take too much of your time. I will go to the conclusions, and if people are curious, I can stick around longer and show you those pictures. So, right. So, okay. Again, this is the result. I've stated it a few times. I want to conclude with one philosophical corollary that I want to deduce from this hardness result. So remember, in the beginning of my talk, I said, look, how did we choose to lay the foundations of deep learning? We said, look, we have this powerful algorithm, gradient descent. We have a lot of data. We have supercomputers. So now what we're going to do is we're going to write down complex models of the world and train them in our supercomputers using a lot of data. And we're going to do gradient descent to do that. And we were sort of semi-agnostic about what models we will write down. So I claim that there are obstacles down the road if you want to lay the foundations of multi-agent deep learning. And in particular, you cannot just follow the same recipe. In particular, you have to be much more careful in how you model the multi-agent learning setting that you are targeting. You have to spend a lot of thought on what are meaningful solution concepts. You have to choose the architecture cleverly, and you have to potentially use domain knowledge there. And you have to spend time in designing your optimization algorithm. And I claim that then and only then will you be able to get other successes like the AlphaGo algorithm. And in particular, I would like to point out that AlphaGo was not the result of just doing, like being blindfolded and doing gradient descent on some very complex model. It does use a lot of the game theoretic understanding around how to solve complete information, turn-based, two-player, zero-sum games. So it's using a lot of that knowledge in the construction of the algorithms, not just, like writing a very complex, function that maps the board to what action to take next and just hitting it with gradient descent in supercomputers. It does use some of the understanding we have about these games. So again, I think that, replicating those types of successes going forward would require a lot of thinking around modeling the problem, choosing the solution concept, writing down the right architecture, and working on our optimization methods. So this is sort of like a very interesting line of work. We are thinking about that in various ongoing collaborations. So, like with the same players plus Noah Golovitz, who's another PhD student, we are thinking of asymptotically convergent methods in general, min-max, non-convex, non-concave problems, where again, we know that polynomial time is out of the picture. So we're shooting for just asymptotic convergence, which hopefully has better practical behavior. On the more structured side, which is motivated by what I just talked about, we are thinking of special cases of two-agent learning problems, where we hope that extra structure in the problem can allow us to converge to global solutions. One of my favorite types of such settings is two-player zero-sum reinforcement learning settings, where even though the function is not convex-concave, work of Shapley has shown that min-max equilibria do exist. And sort of like in this recent New York's paper with Dylan Foster and Noah Golovich, which have shown that, two timescale, policy gradient methods converge to those solutions. So in general, the problem of multi-agent equilibrium computational learning is very fertile. It's very virgin and like a very fertile ground. And, I encourage you that to all think about it, because I think, it is really important for laying the foundation of a future that, will arise once, you consider learning agents interacting with each other in the wild world. And that's basically it. I'm happy to stick around for questions and stuff. Thank you very much.